Hello, this is Cliff Jordan. Welcome back to our series, our data science series on linear regressions. You're in part 3 of that series. And in parts 1 and 2, we talked about the data, and then we also talked about how to generate the Pearson Correlation, which I will show you right here. Here's what the Pearson Correlation looks like. N, by the way, is the number of samples. Y bar, it means the mean Y. X bar is the mean X, and so on and so forth. But we've talked about in the last video exactly what all these values are, and we manually calculated them over here. So these are the calculations of those, and then we were able to manually calculate the Pearson Correlation right here. Now remember, the Pearson Correlation goes from -1 to 1. 0 means it's uncorrelated, meaning that X goes up and down. It doesn't really have anything to do with Y going up and down. They're just not correlated. +1 correlation means every time X goes up, Y goes up approximately the same amount, or a ratio of the same amount. A negatively correlated, -1, on Pearson Correlation means that every time X goes up, Y goes down the same amount all the time. Okay, so that's what the Pearson Correlation is. Extremely important for us doing linear regressions. That said, what we're going to now do is we're going to go fill in some of these other variables that we need. So this variable here we need is just the count. The count or N, how many samples or rows of data do I have? Well, I already told you I got 84 different purchase dates, so that is 84. And what you can do is, in Excel, you can just do a count on the purchase date, and what that will do, that'll give you a value of 84. Okay. Now, the next thing we're going to talk about is called degrees of freedom. Now, degrees of freedom is kind of a very hard thing to understand, but it's related to two things. It's related to two things. One, it's related to the number of rows of data that you have. And the second thing that's related to is the number of independent variables that you have. In our case, the dependent variable, and you're going to hear this in data science, the dependent variable often is what we're trying to predict. And so for us, and most often that's what we would call well, let me say it this way. In the world of linear regressions, that's what we call the Y. So the Y column is our dependent variable. The independent variable is the X column, okay? And that's just referred to as the independent variable. The Y column being called dependent variable, it makes sense because it depends on X, right? And I could have several different variables. Maybe I have coupon values 1, what gender he is, he's a guy. I could have another variable meaning the day of the week, or the time of day, etc. And maybe all of these might impact the total purchase amount. Okay, but so I could have multi-variables. But in this particular case, in this example that we're doing manually, we're just going to use one independent variable, which is the coupon value. So, like I said, degrees of freedom depend on two things: the number of rows of data that you have, and the other is the number of independent variables. Well, I've got 84 rows, and then what you have to do is you have to subtract one row for the number of rows of data that you have. I don't know how to explain exactly why. I would probably have to go look it up and try to figure that out. But the other is we also take away 1 for the number of variables. And so we have one independent variable. So it would be 84 minus 1 row minus 1 variable. That's 82. So if you look up here at the degrees of freedom, and let me just uncover that, but it's basically set up to whatever the count is minus 2, and it's 82. All right. This is important. You may not understand why. You'll kind of get a good feeling of this as time goes on, but there's certain things that get penalized if you don't have enough data, and this is where the degrees of freedom come in. You also get penalized if you have too many variables when you're doing certain types of regressions or certain types of not regressions, but predictions, or using different types of formulas for predictions. So the degrees of freedom are very important from a statistical point of view. That said, the next thing we're going to calculate is the standard deviation of x. Now you say, well, what is standard deviation? Well, I think we talked about this a little bit in the, I think the normal distribution video, which was kind of a precursor here. I didn't go into detail how you calculate standard deviation, but I will today. And if you look at the formula up here, it is the square root of f5, which is the sum of the delta x mean squared, divided square root of the f5 divided by I3, which is the number of rows, minus 1. Okay, and this minus 1 is, the I3 minus 1 essentially is degrees of freedom, but it's only looking at degrees of freedom related to the number of rows, not to the number of variables. So, you take the square root of the delta x mean squared divided by the number of rows you have minus 1. Okay? And when you do that, you end up with, and I did something wrong. Let's see what I did wrong. Okay, I corrected it. There we go. Bingo. So here's our standard deviation. So the standard deviation of the x is actually 3.36, which means that the average coupon, or we know the average coupon was right up here at $2.27. But standard deviation, think of it as kind of like a plus or minus. So it's like 2.27 or $2.27 plus or minus $3.36. Yeah, you can kind of think of it that way. Okay, it's kind of a margin of variance, but it's called standard deviation. Okay, I'm not going to go into depth because if you want more understanding on that, go back to that video on normal distributions. We also take the standard deviation of y, which is the same formula. You take the square root of the delta y means, the sum of the delta y means squared, that's the f6 value, and then we divide it by also the number of rows minus 1. Okay, so there we get $25.41. So which means he spends, on average, which was right here, $109 plus or minus $25. Actually, his range is a little bit more, but it depends on certain numbers of standard deviations on the y. But that is the standard deviation. Okay. We are now ready to calculate the two most important things of the linear regression, and that is the estimated slope and the y-intercept. So let's look at estimated slope. If you look up here, here's the formula. The formula is F8, which is the Pearson correlation times the standard deviation of the y divided by the standard deviation of the x. So it's this r times the y divided by x. So, and if I cut you over here, you can kind of see that. There it is. The slope is m. R is the Pearson correlation. Okay. And the SY is the standard deviation of y, and the SX is the standard deviation of x. So here I actually got it backwards. I said slope is equal Pearson's times the standard deviation of x divided by the standard deviation of y, and that should be standard deviation of y divided by the standard deviation of x. So we're correcting things in real time. Can't get better than that. So let's go back to our tutorial or the actual spreadsheet, and let's go ahead and highlight this. There we go. So in here it's calculated as 2.41, okay, which, like I said, it's the Pearson correlation times the standard deviation of y divided by the standard deviation of x. And 2.41, well, how does that measure to what we calculated on the graph? Remember that formula we had on the graph that you haven't seen for a couple of videos? There's the graph. And so here's the actual scatter plot of the data that we're looking at, and look at the actual equation of the trend line. And remember, I told you the trend line itself is the linear regression, right? So the equation of the trend line gives us 2.4132. That is the slope of the trend line. which is, if we go back, that's the slope that we just calculated. So we are accurate. We're right on. We got the right formula here. This works. Okay. Let's look at the y-intercept. Well, this is dependent on the F4, which is the y mean, minus I7, which is the O. All right. So to calculate the y-intercept, let's go back here. It's real easy. All you have to do is take this is the y-intercept b, that's equal to the average y, or the mean y, minus the slope that we just calculated, times the average x. Bingo, piece of cake. This gets back to that formula of y equals mx plus b. It's just switched around a little bit, and we threw in the average y and the average x. It works, so you can use this. All right, let's go back to the formula, or to the spreadsheet, and let's uncover this. That's what we did right here, and bingo, we get $103.66. If we go back to the scatter plot, voila, there is our b that we just calculated manually, and it matches what Excel figured out. It is $103.66. We did it manually, and it works. And now you can go back, because of this, you can go back and you know exactly how to do all this manually. So let's say you wanted to write a Python program to do it all manually, you could do that. I don't know why you would do that. There's lots of APIs, there's lots of libraries that do that for you. But if you wanted to, you could do it. You could write an assembler program, make it super fast, super fast. All right, that said, what we're going to look at is the R-squared value. Now, R-squared is a measurement that helps us understand how well the trend line accounts for the variance in the actual data. That's kind of the technical term for it. What a real easy to understand way is just saying how much the trend line fits the data. Okay, so the R-squared value is simply, you may ask, well, why do we call it R-squared? Well, we call it R-squared, let's go up here, because it is essentially R-squared. R is Pearson's correlation, right? And so we take that and we square it, and we get R-squared. Now remember, Pearson's correlation, I told you that was important. Pearson's correlation is extremely important. Now, Pearson's correlation goes from -1 to 1, right? Now, if I square it, all the negatives become positive, right? So now our squared value only goes from 0 to 1, okay? The closer you are to 1, the stronger the R-squared value is, which means the stronger the correlation is between your independent variable and your dependent variable, the x and the y, okay? So what we want to see is, when we do some modeling, we want to see an R-squared value that is close to 1. The closer it is to 0, that's bad, okay? So that's why I say here, the higher the better, okay? By the way, R-squared has another name, and it's called the coefficient of determination. Now, before we end this little video, I want to show you really quick the relationship between R-squared and the amount of variance in the data. So to do that, let's go back to the graph. And what I'm going to show you here is, if you see here, let's go back right now. Right now, this is the scatter plot of the data. I get an R-squared of 0.10. That's 10%, or 0.1. That's closer to 0 than it is to 1. That's not very good, okay? Now, but the reason that is because there's a lot of variance in the data. All these points are like really high and really low above. What we're going to do is we're going to take out some of the variance. Right now I have a variance set to 40 on the data, $40, $100 plus or minus $4. Let's make this $10. $10! There we go, $10. Now I hit F9 to regenerate all the data. Let's go back to the scatter plot, and what do we see here? We see that the data is no longer as variant around that trend line. And because of that, the trend line more accurately depicts the variance or accounts for the variance in the data. And because of that, look what happened to the R squared. It went up. Okay? So when you have highly variant data, your R squared is going to go down on a linear regression. If your data is not so highly variant, your R squared is going to go up. That said, let's go to the next video. Ciao.